we had stopped at this point here where we were looking at the different functions that can be created. We spoke about some of the different principles that we try to implement with our code and with the abstractions that we build with functions. So we said that we're striving for modularity, where whatever module we create, whatever function we create, is going to be doing one thing and one thing only. We also spoke about reusability, and we said that we want to make whatever we create as reusable as possible. And then we spoke about isolating the details of the computation from its use. So basically, if it is that we are able to call on a sequence of computational steps by a name, then it means then that we don't necessarily have to look at, we're not concerned at that point with the actual steps that are involved. We simply know that this function executes this particular task, and that's all we need to know at that point. So those are the things that we try to strive for. Those are the things that we try to strive for in creating functions. Now let's look at this example that we have on the board here. This here defines a function called larger and one called larger of 3. Let's look at larger first. So looking at larger, can we figure out what it does? If I call larger and I pass some values to it, what does it do with those values? Ultimately, what does it do? What does it do? What is the purpose of that function? It compares the values and it tells us what? It tells you which one is larger. So out of the two things that are supplied, the two numbers that are supplied, just a second. Right, so out of the two numbers that are supplied, it will return the one that is larger. We had looked at examples and we had shown that there are different ways that we can we can present a result to or function that has called on another function for us. This way that they're doing it, they're simply returning the values rather than storing it in something and then returning that something later on, right? So that is one of the alternatives. So it goes through the process of retrieving the values. So let's say we call larger with 10 and 5. It'll put 10 here, 5 here, right? Then that 10 would be right here, 5 would be right here. Is 10 greater than 5? So x greater than y? True, right? So the next line of code that will be executed will be this one. And so it will now exit the function at that point. So it exits with what value? With 10. So here, the value that's going to be returned for us is going to be 10. Now let's look at larger of 3. Larger of 3 takes in 3 arguments, x, y, and z. Now, when we're thinking about if 3 things we want the largest out of 3 things, one way of doing it, you and I could simply just look at it right on and say, if we have the numbers, as soon as we look at that, we know that 15 is the largest out of all of that, right? But we could also have broken it down into smaller chunks and compared 3 against 10, and then compared the result, not necessarily the 10, but whatever the result is, against whatever is left, right? So we could have compared x, y, and z by comparing x and y, taking the largest of that and comparing it against the z, right? So that is what is implemented here on the left. Well, for this function here, it is saying, and if that is the reason, if that is what is actually going to be happening, then it means then we already have a function that can compare 2 numbers, right? So we can reuse that. we can reuse that function called larger and simply call this. So here they're saying, they're taking in those values. Let's say we have 10, 5, and 15. 10, 5, 15. Then if larger, so 10 goes here, 15, 5, sorry. If you have to indicate what? If you have to specify that at the top. All right, so all right, let's take a step back a little bit. The way that that function would be called or invoked would be that I'm going to just write it in the space that I have. I'm going to be using up here because I only have space there. But what it would look like would be larger of 3. And then now you're going to pass in the values. So 10, 5, 15. And the reason now it corresponds with that is because of the order that it was placed in. So the first one goes into the first argument, whatever the first argument happens to be called. Second one goes into second and so on. All right. All right, so we're back to right here. If larger is takes on the values 10 and larger xy now has the values 10 and 5 being passed to it, we have that whole expression here that needs to be evaluated. Do you agree? We have that whole expression to evaluate. Now remember, we have an order of precedence that these things need to be executed in. Do you remember what that order is? Well, PEMDAS, but it's a little bit more extended when it comes on to programming. So in programming, what takes the highest precedence? A function. So therefore, we need to figure out what this function evaluates to, first and foremost. So what does this function evaluate to when it's called with 10 and 5? It evaluates to 10. So basically, as far as this expression is concerned, it can replace this whole thing now with the value of 10. So now it's seeing 10 greater than z. So z has the value of 15. So 10 greater than 15, true or false? False. So seeing that it's false, the next statement to get executed will be down in the else. So it'll come here. And now it will return z, which is going to be that 15. So here it's going to return 15 for us. Right? So that is what has happened. And what has basically happened here is that they've just reused code that existed. So you don't have to go through defining logic for finding the large of 2 anymore because you already have a function that does that for you. All right? So they've simply reused that function that they've created for us. All right, so we saw this example in lecture 1 where we were going through the process of finding the square root of a given number. We looked at the different steps that are involved. First, you start with some guess. Then you check to see if the guess is equal to, is equivalent to the square of the guess is equivalent to x. And if that is the case, then you stop and you return g. Step 3, if you didn't stop and return g, then you need to improve the guess some more and then do it again. So you improve the guess by averaging g and x divided by g. And then you keep improving g until that guess is good enough. So as an example, if you started out with an x being equal to 3, so you want the square root of x when x is equal to 3, then when you call this function, this is the approximate value that you should get back, right? So that's our expectation. That's what we know that we should be getting back from that. Now, let's look at how we would go about doing that. So let's say start with a guess. I'm going to be switching back and forth between this slide on the next one to look at the different steps. So let's just start with the guess. So at this point, we're keeping track of the number of steps that we've done along here, right? And here we're keeping track of the guess in this column. Just a moment. Clem, could you mute your microphone when you're not speaking? We're picking up a little bit of feedback. Thank you. All right, so second column tracks or G. We also have the third column that is just going to keep track of whatever G is after we square it, because remember we're going to be comparing it to see if the G is close to that number that we're starting out with. And we're going to be comparing that G squared against X. So bear that in mind. And we're also going to be keeping track of what the X divided by G is as per what we have here. So it says to improve the guess, we're going to be averaging improve G, sorry, by averaging G and X divided by G. How do you average those two? It's simply adding them up, dividing by 2, right? There are only 2 items in sequence. All right, so that would be this here. This would be the average of the new G. So we're only keeping track of these terms here, so we have quick access to see what those values evaluate to. You guys follow so far? Yeah? All right, so here we're saying that we started out with a guess being 1. If it is that your guess is 1, then when you square the G, then you're going to get 1. Is that close to the number that we're expecting? So we're expecting 3. 3 is our target, right? Is that close to 3? No, it's not good enough. That's not close enough. So therefore, we need to improve the value of our guess. So they say that the way that you're going to do that is to divide X by G. So X is going to be 3, and the guess that you had was 1. So divide 3 by 1, you get 3, right? So that is our X divided by 3 now. Now to form, so now we've taken care of this step. So this step is done. Now we're at this step. To get the new value for G, we need to average the X divided by G, which was this value here. And we need to average it with plain simple G. So we're taking our original G here, and we're taking the new value, the new guess that we had here, the X divided by G, which is that. This is the X over G. Whoops, I don't really look too good. And then we're going to be averaging it. And that now gives us...
Sorry to sir, but I don't think anyone at Kville can see the columns you're referring to, though. We've only been seeing the example larger slide for the longest while. Sorry about that, but we haven't been seeing the columns you're referring to.
Oh, really? All right, let me see if I can stop the share and then restart it, all right?
Thank you, sir.
Sure. Thank you for letting me know. All right, Kville, can you see it now?
Yes, sir. Now we can see everything. Thank you.
Yeah, I'm sorry about that.
No problem.
Sure. So here we are. So now we have the value for a new guess. All of that comes down to the value being 2. So 2 is now our new guess. So we need to evaluate it now to see if it's good enough. So to evaluate our new guess, we're going to be squaring it. So 2 squared gives us 4. 2 squared gives us 4 here. Is that close enough to the value that we are, to our target value? It's overshot the target value. So again, the algorithm says, all right, to get closer to it, then you need to average, you need to divide x by g, and then find the average of that with the original guess. So let's calculate x divided by g. That's 3 divided by 2, giving you the 1.5. And so that's going to be input to the next step going down, right? So this step is now taken care of. We're now at this step in the whole process, this whole algorithm. After we've done the averaging, this is the result that we have. So this is our new guess going forward. When we square our new guess, we get the value 3.0625. We can do a little bit better than that. So we say, no, this isn't good enough. It isn't within the degree of accuracy that we want. So therefore, we proceed to find a better guess. Again, we compute our x divided by g. We get this value, 1.71. So we've now completed this step. So we're now going back again. We're starting again. So this is our new guess. After evaluating it, this is what we end up with. And then now we square it, and this is the value that we get. That is pretty close to what we're looking for. So at this point, we say that we're going to stop, right? And return that this is the square root of g, of x rather, right? So we're going to return this value at that point, right? So what we've looked at here is that we simply have a number of steps that we're going through in order to do that. In natural world, you'd probably just bring out your calculator and that would be the end of the matter to find the square root, right? But if you're implementing a calculator, assuming that you don't have access to a function that finds square root for you, then how would you do it? You would take certain steps that would help you to estimate that value. And this is a reasonable algorithm for allowing you to do that, right? What we see here, and what I described to you before, is that in computing, it really is a matter of expressing the way that you would solve a problem and into programming code. That's all it really comes down to. And so looking at the steps here, this is all English, right? If I told you to do this on paper, you'd be able to do it, right? Yeah. Yeah? Just follow the steps and listen to what it says. So if you can do that, then how can you instruct the computer to do that for you? That is what we cover in this course here. So we're going to look at how we go into the implementation of this. But there are a couple of things that were implied in this algorithm here. One, how do you know when the guess is close enough? It needs to be determined by somewhere. We need to say it's close enough if it is within a certain degree of accuracy, right? So if it's not off by more than 0.001, for example, then if it's not off by that number, then we can say that it's close enough and we can stop there, right? So that's determined by us. How do we create a new guess? Anybody? How do we create a new guess? The average, the g, and the x divided by g, right? So we know how to do that. So if I give somebody that responsibility to say, you over there in the pink shirt, you're just responsible for creating a new guess. What would you need from me to create a new guess? What would you need from me to create a new guess? So look at this. This one here. You need the old guess, right? And you need x, right? And then once you have that, all you need to do is plug that into a formula and you can give him back what the new guess is supposed to be, right? If I ask somebody what is, to figure out if the number that I'm giving you is close enough, what would you need from me? So, gentleman back in the white shirt, what would you need from me if I asked you to determine what is close enough? When the number is close enough? Anybody? You'd need the new, yeah, the guess that you have. And what else you'd need? You need the value of x. And then the way that you would do it, how would you figure that out if it's close enough? You square the guess, and then you compare the guess to the x. And depending on how, or you can find the difference between them. If the difference is very large, it means that it's very different. If the difference is small, and that's determined by you. If we had agreed that we wanted to within 0.001, then you just compare it against that. So you find the difference, and if it's less than 0.001, then you say, yeah, it's fine, right? So you would know how to do that. The other question, how do we control the process of using the new guess in place of the old one? We have some sort of while loop going there. We can imagine that, right? So we have some while loop, it keeps going, and it has a condition. Any while loop or any loop has a condition at which it's going to stop at, right? So the stopping condition would have to say, so each time it goes back into the loop, you have to keep changing that number that it's going to be working with. Because you can look and see here that every single time it comes back. So when it was here, it had a number as a guess. When it looped and came around to here, there's a new value here for guess. So each time it goes around and starts over, it is dependent on a new value for guess. So that value needs to change somehow. We're going to look at how that changes in code. But these are some of the things that we recognize at the stages that are happening. So let's look at this one. If it is that we know that we can just take the value, the guess and the x, and figure out if it's close enough, then we can make that into one module. We can make that into one function, and that function does that and that alone. Done. If we want to figure out how to create the new guess, then we can create a function that does that and that alone for us, right? And then when we're done now, we can simply put all of these things together. So let's look at how we would go about doing that. To determine if the guess is within 0.001, we could implement that function like so. So we create a function called good enough. It takes in guess, and it takes in x. What this is now saying is that, all right, so let's look at precedence here, because precedence is important to recognize with what is being evaluated on this line. Let's say that our guess was 1 and our x is 3. This is the second line that gets executed now. So what is supposed to be evaluated first? Squaring the guess. So it needs to execute this function because we see that this function is inside of the ABS. Why didn't it do ABS first, even though it appears first on the line? Because the one inside needs to provide a value to go into the ABS, right? So this one here has to be evaluated first. So when you square the guess, which is 1, so this now gets replaced with 1. So now we end up with 1 minus 3. And what do we get? -2. So this whole thing here, this whole thing evaluates to -2. What does ABS do? Anybody can figure that out? It finds the absolute value of that. So therefore, D is now going to be storing 2, because that now returns the absolute value of it. Now this statement, so this here is an expression. What does this expression say? What does that expression produce? It produces a Boolean. It produces either true or false. So in this case, D, is it less than 0.001? No, so therefore it will return false. So this expression produces false. And so this function would return false when it's called with these values. All right? So that's what, and we can see that if it happens to be less than 0.001, then it returns true. Cool. So that means we just simply have one thing that we need to call now. So these steps here, these 1, 2 steps here to determine if it's good enough, we don't have to write out all of those. We can simply just write good enough and pass in the values there, right? So if we're looking through code and we just simply see it called good enough, we know that it's returning true or false. It's easier to read because we don't really have to think about the part about good enough yet. We don't have to think about the logic behind that yet, as opposed to seeing a whole bunch of lines. So that makes it a little bit simpler when we can take that out of the equation. We abstract it out. Now let's look at average. We can define a function to find the average of two numbers like so, which is quite simple. It's taking a plus b divided by 2.0, returning the average. Now, note something. Here, they're referring to this, their arguments as a and b. That's fine. It doesn't have to be x and g. Within the context, within the local context of this function, all it knows is a and b. Even if what we're passing from the outside is x and g, when it comes into the local scope, it knows it as a and b. All right? So this here would return the average of the function for us. So we understand that. Now, for improve, what that simply requires, if you're going to be improving the guess, you need to know what the original guess was, and you need to know what the x is that you're trying to get to. And in order to find a new guess, they say that take the average of the guess and take the average of x over the guess, x over g. So that is your new guess. And therefore, you can just return that. Right? So that's improve there for us. So the other part of this problem is that we need to make a decision either to stop or to return the value or repeat the improve operation. So we need to figure out what we need to do there. We can implement a function. We can implement a function to implement this idea of repeatedly doing something. We can define it as, we define improve loop guess x to represent the result of repeatedly improving the guess until it is good enough. So here, we can do it like that. We can do it recursively. So meaning that we're going to be doing those set of steps. If not, we're going to do it again. Using the same instructions, we're just going to do it again. So let's walk through what is happening here. Let's say that we started out with 1 and 3. So 1 being the initial guess, and 3 being your x. So the first thing that we said, the step 1, was to check to see if the number was good enough. How do we know if it was good enough? If we square it, we square the guess, and it's close to the x within the space of 0.001, space of 0.001, then we say it's good enough, and then it will return what? A Boolean, true or false. So when we call good enough, we know that it's going to give us back that value. We don't need to see the code for that. We just know that this function here is going to tell us if it is good enough. So if it says that it's good enough, then the value is going to be true. What do we need to do then? We just send back the value because we reach whatever we need. It's good enough. Done. Right? All right. If it wasn't good enough, then what do we need to do? We need to get a new value for g. We already have that function that knows how to get that better value. It knows that it goes down and it averages so and all that. We're not concerned with that right now. We just know that that function does that. We don't have to think about it. So we just simply call the name of that function and pass the value in. So here improve is past the values that it needs to produce the improved value, and then we move on. So we have our new value for G. Note here, guys, that this return should really be right here. Right? It should be right there. And there's an error in the slide. If it's not there, then Python will complain and say this is an unexpected indent. All right? Right. So this program wouldn't run because of that. So let's assume that that wasn't the case and that it's indented to this level instead. So then now, what we have here is that we're having a function now that says, we're having this statement here altogether is saying improve loop, and it's passing the new G and X. You see that? So what will happen now? What's happening here? At this point, it is going to call on this function once more. You recognize that it's the same name, right? So it's going to call on that function once more with new values this time. So this time it's going to have a new value for G. I think we had said that the new value was what, 2? So the new value was 2. X is still going to be the same 3 that is going to be sent in again. So then it will come down here and figure out if it is better, if it's a better estimate, and if it can stop there. If it can stop there, then it simply says, all right, terminate and go back to wherever it was called. So it would come back to around here, and then now it would return the value. Now let me take a step back. Once it got to this line here for improve loop, remember, in order for it to return something, it needs to get the value for it. It needs to evaluate that expression. In this case, the expression isn't a self-evaluating expression that already has its own value implicit in it. So it's not like it's just saying return 10. And it's not like it's saying return X, which it could just look up and find the value of X. It says return whatever comes back from improve loop. When you call improve loop with the value of 2 and 3. That is what it is saying now. You guys follow? So therefore, it needs to figure out what is produced when it calls improve loop and get back that value and then plug it back into this point here before this one can return a value. It just so happens that the thing that is calling has its own name. It could very well have been another one called improve loop 2 or improve loop 3, and every time you need to drill down, it is calling improve loop 3, 4, 5, whatever, right? But it's the same logic you would put in every single version of it. Every time you're doing it every time you take a step to start over and check, you're going to be doing the same instructions, just like you're doing it with different values. You guys follow? So if that is the case, then you can reuse back the same function name, the same definition here, and it works. So once you move from here and you call it with new values, you can think of it as if it were to call another function, another copy of the function. That function is calling on itself, right? Or you can think of it as it's calling on a copy of itself. So in memory, it has to keep reference to this here and the values that are in there. And then when it calls on itself again, it has to now go to another version of it that has its own code, but with new values for X and Y. So this one calls it with 2 and 3. And that maintains its own set of values and so on. If this one also needs to call on something, then it goes and it calls on another version of it, another copy of it, and so on. And then once it completes what it's doing and it has its value that it can return, then this now closes out, sending back a value. So this might send back a value and say the value is 3, or the value is 1.7. So the lowest that it had drilled down to was 1.7, right? So this one would now return, when it gets to a copy of itself, where it gets to this point, where it's just returning a value, a number. So here, where it's returning that 1.7, in this version of it, it sends that 1.7 along here, going back to this version of the function. This one had a statement that just says return whatever you get back from the function call that you're making. And so this one is going to say, okay, all right, the value that I'm going to be sending back is going to be that 1.7. So that 1.7 gets sent back to where I'd called it before. So it comes to here now. And so this here knows that when improve loop was called with 2 and 3, it's 1.7 come back. It doesn't know that it drilled down into that several times more. All it knows is that when it calls it with 2 and 3, 1.7 comes back. And so this one now is simply going to return 1.7 to the interpreter. Clear? So this here describes the process of a function that's implemented recursively. This is a slight modification to what was done. Again, this should be in this line here. The way that they've done it is to simply combine the two steps. So instead of having two steps here where 1, you produce the new G, and then 2, you make the call with the new G. What they're doing here is to say, this here is step 1. Just get that value, and as soon as you get it, just plug it into the first argument. And then now, this is step 2. This whole thing is step 2, which is going to be to get that, to improve the value and send back the result. So that is one way of solving this problem. There's some other things that we can do for convenience. We can simply say, you can recognize here that while this here would give us the result that we're looking for, which is the square root, it would require, if we give this to some user, it would require that they have to guess a number if they're looking for the square root of x. So if they just want the square root of x, we're going to tell them, so, all right, you want the square root of 3, guess a number and give it to us too. We'll use that. But we want you to guess it and supply it to us. We could save them that trouble and just guess a number and plug it in. No matter what number we choose, if we choose a large number or a small number, it would all converge down to a reasonable estimate anyway. So it don't matter what is chosen. Something just has to be chosen. So we could have chosen to say, let's guess 1 every time and start from there. We could have done that. And so what we've done here is to implement a function to wrap the other one just out of convenience. So we're saying, so to them, all they see is that they just need to call square root with the value that they're looking for, the value that they want to find the square root of. Internally, so inside of the function, what we're doing is to say, yeah, run the improve loop. We know that that will do it for us. But we're going to make it start out with 1 every time. That is going to be the initial guess every time. So the user who's using our function never has to know any of that detail in the background about how that works. And it makes it easier for them to use our function as a result. Right? So if we were to run this, this is what would happen in terms of the function calls that would go through. This would be the list of steps that would be taken. First, they would call on square root, improve loop. From here, it would go down into improve loop with these values. And then because it wasn't good enough, it would end up going down into improve loop again with whatever comes back from this and the 3. And then that still wouldn't have been good enough, so it would go down into that, and go down into that, and go down into that, and so on, right? Once these now produce their values, then the value now gets sent to wherever I'd called it. This value now gets sent to there. This value now gets sent to there, and so on, until square root now has a value that it can produce to the user. All right, so that's the idea behind recursion. But we'll stop here for today. All right? So take a look at the slides. This concept, most students tend to find this a difficult concept. So ensure that you look at the content once you leave here. Make sure you have a good grasp of it. If you don't get it the first time, that's okay, right? So when we come to the next class, we're going to continue with recursion. At least then you'll know what questions to ask about the topic. All right, but chances are if you don't practice it now while it's fresh in your mind, you might get left behind. So to not do that, just spend a few minutes, look at the notes on this here about recursion, and just try to figure it out in your mind. And then we'll continue from there. All right, so that's it for today, guys. Keville, have a good day.
One question, sir.
Sure.
Do you send out by any chance the recordings of the lessons?
I generally don't. I generally don't record. I've recorded the one for last class, and I've recorded this one because I recognize that you guys have been having some difficulty this week. So I was going to make them available to you because of that. So I will do that for the one yesterday, and I'll do that for the one today. Going forward, that's not going to be the case. All right? What is it that you guys have been having?
We're having some difficulties with the classes today, so some of us joining late for this one.
Yeah. What is the difficulty that you're having, though? Because I find that when I join...
I think it was just a hiccup for today. We're seeming to have some kind of organizational issues, but it should be sorted out by next week because we did not have that problem last week.
Okay, but I didn't see anybody in the class on yesterday, on Tuesday.
On Tuesday, we were there, but we saw you join in and join out though that day. I remember that day, but we were there, so I'm not sure what happened at that time.
Yeah, I'm not sure either because I even.
Hi, good evening.
Huh?
Hello.
Yes, hello.
This is KFL speaking. I think the issue is that the students are joining the lecture from off campus. So if there's no one in the lab, you would not see the faculty actually log in.
No, I didn't see anybody at all.
Oh, okay.
Yeah, I didn't see anybody at all. I called Mr. Smith, and I was asking what happened with you guys. I didn't see anybody in the room at all. Is it possible that we have a scheduling issue then?
I am not sure, but is he the person that does the tutorials?
Yes. Yes.
Okay,
Mr. Smith.
He came to the lab, but there are no students in the lab. But they're logged in. I can see some of them.
Okay. All right. So let's hope that next class and the ones following, we won't have that. We'll have everybody done. And of course, if there's something that there's a hiccup at some point, you join and I'm not there, feel free to send me an email. Whenever things like these happen, I'm monitoring my email and my other communication channels to see what might be happening, to see if you guys are trying to get in touch with me. All right? So,
okay.
All right, so I'm looking forward to seeing you guys at the next class. All right. Bye, guys.
Bye.